In today's lesson, we are going to be looking at particular solutions of differential equations, as well as verifying those solutions. All right, starting off, we're given the solution. So the solution for the differential equation is the original function. Remember, in yesterday's video, we talked about how a differential equation is just a fancy way of saying derivative. So the solution of the differential equation is when you're integrating or going back and finding y, or the original function. Given, now this looks like kind of a funky differential equation. Notice we have this y prime notation. There's our derivative. It's just formatted where the derivative isn't solved for. So what we're going to do is find the derivative of the function. I'm going to get all of that writing out of the way so we can see what we're working with, and sub it into our differential equation and show that it's true. Starting off with our y equals e to the negative 2x. And in order to show that differential equation is true, we need the derivative. In this case, they used the y prime notation. Normally, I will not stick with the y prime notation. I don't like it. I think it is confusing, and it's very easy to lose that prime and to get it confused with y. So normally, what I will do is switch it to the dy dx notation. In this particular case, it's not too bad to keep track of, so I will use the y prime notation at this point. Derivative of e to the x is e to the x. So keeping our e function exactly the same, and then we multiply by the derivative of the exponent. So the derivative of negative 2x would give us a negative 2. So there's our derivative. And as I mentioned, what we're going to do next is sub that derivative into the equation. We also have y in our differential equation, so I'll be subbing e to the negative 2x in for y as well. So starting off by rewriting this, 3 times that derivative we just solved for, negative 2 e to the negative 2x, plus 5 times y, that original function, e to the negative 2x, equals, and then finishing off our equation, we have negative e to the negative 2x. Now it's just a matter of simplifying. 3 times negative 2 gives us negative 6 e to the negative 2x. Plus, we've got 5 times e to the negative 2x equals negative e to the negative 2x. And I'm sure you can all see where this is going once we combine those like terms on the left. Negative 6e to the negative 2x plus 5e to the negative 2x does indeed give us that negative e to the negative 2x power, which was our goal. So what this reminds me of, and I know you are all going to love this analogy, but last year in pre-calc or SL1, when we were verifying those trig equations, so we would have two trig expressions that didn't look equivalent, but we would use some trig identities to prove that they are equivalent. Kind of doing a similar thing here, but with derivatives instead. Notice in our second example, our differential equation has the second derivative in addition to the original function. So what we're going to do is differentiate this function twice. Again, this one is using that prime notation. In this case, it doesn't bother me too much, so I'm going to stick with the prime notation. So the first derivative of our function, and both of those c's, c1 and c2, are just constants. So what we're really showing in this case is that for any multiples of this original function, or a multiple of sine and a multiple of cosine, that this differential equation will always be true. So we're treating those c's like coefficients, just numbers that come along as we take the derivative. So we'll have c1, derivative of sine is cosine, And then derivative of cosine is negative sine. So I'm going to cancel that negative as I go. So plus that c2 times sine of x. Taking the derivative again, that c1 is going to go along, but this time my derivative of cosine is negative sine. So we'll have negative c1 times sine of x. And the derivative of sine is positive cosine, so we'll have a positive c2 times the cosine of x. All right, subbing that into our differential equation, we've got negative c1 times the sine of x plus c2 times the cosine of x plus our original function. So now I'm subbing in that c1 times the sine of x minus c2 times the cosine of x, and showing that all of that is equal to 0. I apologize for the terrible handwriting. I know my handwriting isn't awesome to begin with, and my tablet, there's a delay between it connecting or communicating with the computer, so it's super hard to try and write nicely. I apologize for that. Hopefully you can see as we combine our like terms that negative c1 sine of x will cancel with our positive c1 sine of x, and our positive c2 cosine of x will cancel with our negative c2 cosine of x, leaving us with 0 equals 0.